In the last session, we had an idea about what is memory hierarchy. To quickly recall, we discussed about the purpose of auxiliary memory or secondary memory. You transfer data and program from auxiliary memory to main memory or primary memory because it is faster than auxiliary memory. And CPU can fetch or get data or program for manipulation or for processing from main memory. But in between main memory and CPU, we have got one more memory that is called cache memory. You know pretty well, the cache memory is meant for speed. It has been introduced as an interface between your CPU and main memory just for its speed. If data or program is available in cache, it obviously reduces the waiting time of CPU. When the waiting time of CPU gets reduced, its busy time gets increased or its performance factor gets improved. In other words, to improve CPU's utilization or throughput, we have cache memory introduced. You can imagine a computer system with and without cache memory. If cache memory is present, the performance of CPU factor gets increased or throughput gets increased. If cache memory is absent, it is relatively less. So that's the difference between the presence or absence of a cache. And of course, you know, cache memory is made up of static RAM, which uses transistor as its base. Now let us come to another important topic of this session, namely ROM. Of course, you know, ROM is known as read-only memory. While ROM chips are produced by the manufacturer, its contents are also written. ROM is meant for storing a program known as bootstrap loader program. I have already made you to know what is a bootstrap loader program. It's a program that is kicked off or that gets started when you switch on your computer to transfer the essential portion of operating system from auxiliary memory to primary memory or to your RAM. And this program is permanently stored inside a chip called the ROM chip. And this program is made available permanently on ROM. And whenever you switch on your computer, it loads, this bootstrap loader program gets activated, it starts running, and in turn, it is bringing in the necessary part of operating system or OS from your auxiliary memory to primary memory. Only when OS gets loaded onto your primary memory, it makes your computer system to get ready to accept user commands and process it. So that's the fundamental principle, keep in mind. When you come across ROM and RAM, you know the difference between them. In RAM, you can perform both reading and writing, whereas in ROM, you can perform only reading. Here, writing is possible. In ROM, writing is not possible. RAM is volatile, ROM is non-volatile. And the size of ROM is also relatively less when compared with RAM. RAM capacity, I told you, it is in terms of few GBs, whereas in ROM, it could be in terms of MBs. Okay. When you come across this RAM and ROM, they are basically IC. We normally call them as integrated circuit. Shortly, we refer them as chips, integrated chips or integrated circuit chips. If you consider a typical RAM chip, for example, I wanted to consider a RAM, which is having 7-bit address. When you go in for a 7-bit address, how many locations are possible? Using 1 bit, you can identify 2 locations, namely 0 and 1. Using 2 bits, there are 4 combinations possible. That means you can denote 4 memory addresses, namely 00 represents memory address 0, 01 represents the memory address 1, 010 represents memory address 2 in decimal, and 11 represents memory address 3. Therefore, using 2 bits, you can identify 4 locations. That means it is 2 power 2. When there are 3 bits, you can identify 8 locations. 2 power 3, that is 8, which runs from 000 to 111. You can quickly recall, since you know the number system. 000 denote decimal number 0 and 111 representing decimal number 7. From 0 to 7, there are totally 8 patterns available, and these 8 patterns represent 8 different memory locations. In other words, using 3 bits, you are able to represent or denote 8 storage locations. Using 7 bits, how many storage locations can be identified or capacity can be determined? 2 power 7. 2 power 6 is 32. 2 power 5 is 32. 2 power 6 is 64. And 2 power 7 is 128. That means using a 7-bit address, you are able to have 128 storage location. That's why it is marked as 128. And what is this 8 standing for? This 8 represents how many bits can be transferred, or what is a word length, how many bits can be stored in the memory location. There are 128 locations, and each location can store 8 bits. Why it is only 8 bits? Why not more? Because the processing capacity of the computer is 8 bits, or it's 8-word computer, or the word length is going to be 8 bits. Therefore, it is going to be 8 bits. So therefore, address bus is 7 lines, and data bus is going to be 8 lines. In other words, your address bus consisting of 7 lines, and your data bus is consisting of 8 lines. You know, address bus is unidirectional. It always goes from CPU to memory. To identify a location, first use the address bus, place the storage location address on the address bus. It is transferred from CPU to memory. And then data bus is bidirectional. We know pretty well it can flow in both directions, either from memory to CPU in the case of reading operation, memory to CPU in the case of reading operation, and CPU to memory in the case of writing operation. That's why you have got 2 signals, RD standing for read and WR standing for write. Of course, instead of using 2 different control lines or control signals to perform reading and writing, you can have a single signal. By if the bit is 0, you can say it is read operation, and if the bit is 1, it can be write operation. You can reduce the number of lines by combining these 2 operations to be a single line. That means if the bit is going to be 0, it denotes reading, and if the bit is 1, it denotes or it refers to writing. But here in the example cited, we have got 2 control lines, or 2 lines are available, one for exclusively for reading and another one exclusively meant for writing. And now you know there are 128 storage locations. To identify each location, we require 7 bits, and the address bus is 7-bit long. It's a 7-bit address. And data bus is going to be 8-bit long. It is going to be data bus is going to be bidirectional, because data can flow from memory to CPU in the case of reading operation, and CPU to memory in the case of writing operation. It is bidirectional, whereas address bus is always unidirectional. Keep that in mind. And there are 2 control signals, reading and writing. Apart from that, we have got 2 more lines available. One is called chip select 1 and chip select 2. Why you have got chip select 1 and chip select 2? For example, I want to increase the storage capacity. I want to increase the storage capacity to 512 MB RAM. In that case, each chip can store only 128 bits. To have 512 MB RAM size, I have to have 4 RAM chips. Each RAM chip can store 128. Each RAM chip has got 128 storage locations. To have 512, I require 4 such RAM chips of size 128 by 8. Don't bother about these 8. This 8 is nothing but your word length. In other words, the capacity of your database. Okay. How many storage locations are there? 512 storage locations, or I require 512. That is going to be the size of my RAM. Since my RAM chip can have only 128 storage locations, and each location storing only 8 bits, I have to go for 4 such RAM chips. To select a RAM chip, you can make use of the chip select 1. You can ask me, what is the purpose of the chip select 2? For example, I told you, we have both RAM and ROM stored inside the computer. When you start the computer, we have to activate ROM, and within ROM, we have got a bootstrap loader program that should be triggered, that should start running. To select whether the address is meant for, whether you want to select RAM chip or ROM chip, you can make use of another chip select line that is called chip select 2. Therefore, whenever you're going to have multiple chip select lines, it is meant for denoting a RAM chip or a ROM chip, or if it is going to be a RAM, this can decide whether you want to select chip 1 or chip 2 or chip 3 or chip 4. That is a purpose behind it. The purpose of read signal is the read line is meant for reading, and write line is meant for writing. And the 7-bit address is to denote 128 storage locations. And of course, this is going to be 8-bit database, and it is bidirectional. You can see the direction mark here. It is bidirectional. That means data flows in both directions. Okay. Now, whenever you're going for, you can see here CS1 and CS2. Remember, a location can have the values, 3 different values are possible. Either it can be 0 or 1, or it is a don't care condition. Don't care means it can memory function can be anything. It could be, we normally call them as the high impedance state, generally we call. I don't know how many of you know about tri-state buffer. Buffer can store, buffer means either it can be 0 or 1. There is one more concept known as a tri-state buffer. it can be in 3 different states: 0, 1, or high impedance state. So that is the basic idea here. We have a status called as the high impedance state. See here, when chip select is going to be 0 and no chip select line, if it is going to be 0 means no chip is selected. Only when it is 1, the chip is selected. So if it is 0, irrespective of whether it is the second chip select 2 is either 0 or 1, no problem at all. When the chip is not selected, we are not bothered whether we perform reading operation or writing operation. It will be going to the high impedance state. That is called as the inhibit state. When the chip select is 1 and chip select 2 line is going to be 0, when read is 0 and write is also 0, that means I'm not performing either reading operation or writing operation. Both are going to be 0. In that case, it is also reflecting high impedance state. Now, when the chip select line is 1, that means I'm enabling the chip, namely the RAM chip. When this is going to be 0, chip select 2 line is going to be 0. You know what is 0 bar? 0 bar is 1. Whenever you send a low signal, you take the complement of it, it becomes 1. Therefore, the chip gets activated. Then, when R is going to be 0 and write is going to be 1, you are performing writing operation. That means input data to RAM. That means data is sent from CPU to RAM. The same thing 1, 0, read signal is 1 and write is not there. If it is when the read signal is going to be 1, yes, this has to be 0, keep in mind. Then you are performing a reading operation. When you perform a reading operation, data goes from RAM to CPU. That means your output of RAM is sent to CPU. That's what is output data from RAM. That means data is sent from RAM to CPU. When both are going to be 1, then both are going to be 1, it is going to be high impedance state. So keep in mind. So only when chip select 2 is going to be 0, you are going to the chip is selected. Only when chip select is 1 is only when the chip select 1 is going to be 1, the chip gets selected, and the second chip select 2 input has to be 0. Then only either reading operation or writing operation is done. Otherwise, in all other cases, it goes to a status known as what? Inhibit state or high impedance state. So this is the point you have to keep in mind. And this is called as your function table. Okay. Now, the same can be demonstrated with the help of the diagram. We normally call them as memory address map. For example, I want to construct a 1024 by 8 memory consisting of both RAM and ROM. 1024, you know pretty well, each RAM chip can hold only, the RAM chip example which we considered earlier, it can store only 128. And I have a ROM chip whose capacity is 512. Therefore, I have to have 512 MB of RAM, or 512 locations in RAM and 512 locations in ROM. That means there must be each RAM chip is going to be 128 storage locations. To make it 512, I require four such RAMs, and I require only 1 ROM. Okay, let us go in for the diagram. It becomes easy for you to understand. Let me quickly elaborate here. A ROM chip, as I mentioned before, is going to be 512 by 8. Chip select 1, chip select 2, 9-bit address. Why? What is 9-bit? 2 power 9. 2 power 7 is 128, 2 power 8 is 256, and 2 power 9 is 512. And the data bus remains the same. It is going to be 8 bits. Remember, in ROM, the data doesn't flow from CPU to memory. Data always, you can only perform reading operation. Writing operation is not possible. Therefore, it is only unidirectional. Data is output from ROM, and that is being sent to the CPU. So that's the point you have to keep in mind. Let us go in for the hardware circuitry. Before that, keep in mind, memory addresses are denoted in hexadecimal number system. You know, there are different number systems. You know, you would have come across the conversion part of it, etc. Decimal number system, binary number system, octal number system, and hexadecimal number system. Memory addresses are denoted in hexadecimal. You know, in hexadecimal, there are 16 different digits, 0 to 9, and 10 to 15 in decimal is equivalently represented as A to F. Capital A, capital B, C, D, E, and F. So remember, memory addresses are always denoted in hexadecimal memory, hexadecimal notation. Memory addresses are always in hexadecimal notation. That's a point you have to keep in mind. Let us go in for the construction. As I said before, I want to have a memory of 1024 by 8, of which 512 locations must be RAM and 512 storage location must be ROM. We have seen the ROM, typical ROM. ROM is going to have 9-bit address, and then chip select line 1 and 2. Let us come across the diagram. So this is going to be the RAM, RAM 1, RAM 2, RAM 3, RAM 4. Why there are 4 RAMs? Because each RAM can store only each RAM chip can hold only 128 storage locations. Since I require 512 storage locations, there has to be 4 such RAM chips. Chip RAM 1, RAM 2, RAM 3, RAM 4. And these are the hexadecimal address, you know pretty well. You know memory addresses are hexadecimal. You can count how many hexadecimal digits are there. There are 8 hexadecimal digits. 00000007F. F means 11111. You know how to convert hexadecimal to binary? It's a 16-bit address. Okay. So let me not go over there to this part of it for the time being. Let me come to straight away to the diagram. So this is what I want. So this is your database, read signal, write signal. This is your CPU, and this is the address bus. Address bus is meant for carrying address, and data bus is meant for carrying data. Let us take up the same example. You know pretty well, ROM chip has got 512 storage locations, and its address bus is going to be 9-bit long, 9-bit address bus. Okay, let us come to the same example. It will be easier. 1 to 7, these are the address bits. 1 to 7 means using 7 bits, how many storage locations can be identified? 2 power 7, which is 128. Therefore, the address bits 1 to 7 are meant to denote RAM. 1 or locations in RAM 2 or locations in RAM 3 or locations in RAM 4. Because each RAM chip has got 128 locations. The address bits or address lines 1 to 7 take care of the 128 storage locations present in each and every RAM. That remains the same. Bit number 8 and 9 are meant to denote which RAM chip has to be selected. That is decided by CS1. Now you can see here, I'm making use of a decoder. You know what a decoder is? It decodes a given address and then decides the output. Here, if you look at the decoder, it is a 2 to 4 decoder or 1 out of 4 decoder. 2 to 4 decoder means it has got 2 input lines, that is represented as 8 and 9. It has got 4 outputs, 0, 1, 2, 3. If the input lines 8 and 9 are 0, 0, 0 gets selected. If it is going to be 0, 1, 1 gets selected. If it is 1, 0, 2 gets selected. If it is 1, 1, 3 gets selected. See here, if it is 0, it goes chip CS1. That means chip number 0. If it is 1, it goes chip number 1. CS1 represents chip number 1. CS1 remains the same. If it is 0, it goes to the first chip. If it is 1, it goes to the second RAM chip. If it is 2, it goes to the third RAM chip. And if it is 3, it goes to the fourth RAM chip. So 0, 0 means first RAM chip. 0, 1 means second RAM chip. 1, 0 means third RAM chip, this one. And 1, 1 means the fourth RAM chip. Fine. Therefore, the chip select 1, CS1 is meant to select which RAM chip has to be selected. Look at here. Look at the 10th bit. The 10th bit is 10th bit is supplied here straight away. 10th bit is supplied here. Look at the 10th bit. The 10th bit is meant to decide on your chip select 2, CS2. As I mentioned before, are you going to select RAM or ROM? Look at here. If the 10th bit is going to be 0, see the arrow mark or my cursor position. If it is 0, it goes to CS2. What is 0 bar 1? Therefore, if CS1 is going to be 0, the first chip is selected. If the output of decoder is going to be 0, it is enabling CS1 of first chip. And CS2, since the 10th bit is going to be 0, 0 bar is 1. Therefore, 0, 0, 0, 0 in the 10th bit, 0 in the 9th bit, and 0 in the 8th bit, it enables RAM chip 1. 0 in the 10th bit, 0, 1 in the 9th and 8th bit, it enables chip number 2. Similarly, 0 in the 10th bit, 1, 0 in the 9th and 8th bit enables RAM number 3. If it is going to be 1, 1 and 0 in the 10th bit, it is going to enable RAM number 4. Now let us come to the very important point. If the 10th bit is going to be 1, see here, it straight away comes to inverter inverts an AND gate. So 1 becomes 0, it enables ROM. ROM has got how many lines? There are 9 address lines. We have already considered a ROM whose memory size is 512. So the idea is we are building a memory with 1024 storage locations with 512 of RAM storage and 512 locations of ROM storage. When you come to RAM storage, each RAM chip can store only 120. Each RAM chip has only 128 locations. Therefore, we make use of 4 such RAM chips: RAM 1, RAM 2, RAM 3, RAM 4. So 00 of bit number 8 and 9. If the address bus line numbers 9 and 8 or 8 and 9 are consisting 00, it selects RAM 1. If it is 01, it selects RAM 2. If it is 10, it selects RAM 3. If it is 11, it selects RAM 4. But keep in mind, the 10th bit must be 0. If the 10th bit is 1, you are not selecting a RAM chip, you are selecting a ROM chip. And what is the size of ROM? 2 power 9. So all the 9 bits, see here, all the 9 bits, 1 to 7 comes to ROM. And the address bit numbers 8 and 9. 8 and 9, you see here, these two are also coming to ROM. So therefore, 2 power 9 is 512. There are 512 storage locations in ROM and 512 storage locations in RAM. And this is how you have a memory connection to the CPU by building a 1024/8. What is meant by 1024/8? There are 1024 storage locations, of which 512 are RAM and 512 are ROM. And the data bus is going to be 8 bits. And data can be bidirectional, whereas in the case of ROM, it is unidirectional. See here, it is only unidirectional. Data goes out of RAM to the CPU via data bus or through data bus. Whereas in the case of RAM, the data bus is bidirectional. It goes to a database. From database, it goes to the CPU. This is a basic idea behind the concept of your address mapping or memory mapping. In the next, of course, in the next part of it, before we conclude, I want to give a brief idea about different types of ROM. You know, ROM is a permanent storage, and it is used for storing programs which are system software in nature. For example, bootstrap loader program. I told you there are 2 different types of ROM. One is known as PROM, and the second one is known as EEPROM. What is a PROM? Programmable read-only memory. In the case of ROM, you can perform only reading. Writing operation is not possible. But if the user wants to write something onto the ROM, instead of accepting the manufacturer's program, I want to write my own bootstrap loader program. If that is the case, then you can buy a PROM chip, programmable read-only chip. You can write once into the PROM chip, and then you can read it any number of times. That's the basic idea behind the PROM. In the case of PROM, there will be a mechanism called as extra PROM write. Special writing device is required to write into PROM, and there will be a fuse available. All the bits are initially 1, which is representing all the. How do you represent the storage? It will be done by a matrix. I can put that way. Rows and columns, you know, in the case of mathematics, rows and columns are there. Row number 0 to row number m. That is, we have m by n. M words are there, and each and every word is going to be n bits long. We generally call it as a m by n matrix. 0 to m will be the rows, and 0 to n will be the columns. So the intersection of a row and column is called as a cell. There will be a fuse available, and if the fuse is burnt, it represents 0. If the fuse is not burnt, it represents 1. In other words, if the fuse is present, it represents 1. If the fuse is absent, it represents 0. By initially, everything will be 1. Whenever you write your own code, you have to make use of a special device and then pass a minute electric current to, let me say, nullify or diffuse the fuse present there at the intersection of a row and column. That is what we call them as a cell. This is in the case of a PROM. So technical details are not required. You can remember in the case of PROM, writing operation is possible. You do writing with the help of a special device. By default, all the cells will have the value 1. To make it 0, you have to pass a very minute current, namely milliamperes or microamperes, to nullify the fuse or to remove the fuse. This is in the case of a PROM. In the case of a ROM, we have a diode present. Of course, I can go for ROM. The intersection of a cell will have a diode. If a diode is present, it represents 1. If diode is absent, it represents 0. The presence of diode denotes 1 bit, and the absence of diode represents or denote 0 bit. In the case of EEPROM, we can perform both reading and writing into the same ROM chip. That is done with the help of electrically erasable read-only memory by passing electricity. You can erase the contents. First, what you do, get to your ROM chip. All the bits will be 1. Write some programs into it. Let me call the system software programs. After some point of time, we feel These programs are outdated. You want to write a new software program. Therefore, what you do, erase the contents. The contents can be erased by two ways. One is by passing electricity and the other by passing UV rays, ultraviolet rays. If you pass UV rays, it is called UV EEPROM. I'm sorry. If you pass electricity, it is called electrically erasable programmable read-only memory. Electrically erasable programmable read-only memory. It is shortly referred as EEPROM. If it is going to be UV EEPROM, it is ultraviolet erasable programmable read-only memory. So that's it. That is in short and sweet about your PROM, ROM, and EEPROM. Remember, the presence or absence of a diode represent bit 1 or bit 0 in the case of a ROM. The presence of a fuse represent 1 or 0 in the case of a PROM. In PROM, writing is possible once, but after that, writing is not possible. You can only perform reading. That's the reason why a PROM is also known as write once, read many times memory. In the case of EEPROM or UV EEPROM, you can perform reading and writing as many times as you want. So that is about ROM. Let us stop in this session. In the next session, we will start off with the important types of memory, namely associative memory, cache memory, and virtual memory. We can see in the subsequent sessions. Thank you.